Hi, my name is Kylan Shinmoto.
And my name is Rowan Fitch, and today we're going to give you a presentation on summarizing shelter-in-place orders.
Okay, so our goal is to summarize these shelter-in-place orders because we found that sometimes shelter-in-place orders can be too long or cryptic. For example, Rowan had trouble understanding all the details of the California shelter-in-place order, and we're unsure of some of the rules, and people are confused as to what they can or can't do, which is why we want to do this thing.
So our goal was to use some of the concepts we've learned in this NLP class to summarize as many shelter-in-place orders as we could get within the US. And then as like a final step, we sort of grabbed common sentences from the summaries that we created that kind of created an overall general guideline for like shelter-in-place orders across the United States. So our method of text summarization was extractive, which means that the summary actually only contains text from within the original document. Now, as far as NLP goes, that's usually how a summary will be, because you can sort of find some way to numerically represent text within a document and rank it. Whereas a summary written by a human is usually abstracted, which means that the concept behind the summary and the original document may be the same, but the summary and document may not actually share that many of the same words.
Okay, so the first step we need to take in order to create these text summaries is to collect our data. And we did this by going to an article by New York Times that had all the different shelter-in-place orders listed from all the states that have issued shelter-in-place orders. And we collected PDF files of the official orders. And we also collected summaries of these shelter-in-place orders that were done by local news stations. And these would be our human summaries that we would use to compare our text summaries to. And to do this, we also converted all of our shelter-in-place orders, the official orders, and the local news station summaries into text files.
All right, so the main method we used was vector word embedding. So what that is basically every word in a document is represented as a vector. And to streamline this process, we use this resource called GLOVE. It's a Stanford NLP resource. And what it is it's a list of over 6 billion words that have been represented as vectors. And what that did is it just made the process of converting each word into a vector a lot easier, because we could just use this resource to look at the table. So basically what we did is we took every sentence in a document and represented that sentence as a vector, where the vector that represents the sentence is an average of all the word vectors within the sentence. Now, I know that sounds a little confusing, so if you're more of a math person, this little equation right here might help you understand. So if we let S be the sentence, then the sentence vector is equal to the sum of all the word vectors within the sentence divided by the number of words in the sentence. So after you compile all those sentence vectors, you create a matrix that's n by n, where n is the number of sentences in the document. And that matrix is populated by the cosine similarity of two sentence vectors. So the matrix at index I comma j is equal to the cosine similarity of sentences I and sentence j. And this matrix right here is actually, it's obviously a lot longer, as you can see by the dots. It's actually the Alabama shelter-in-place order represented as one of these matrices. So after we created those matrices, what we did is we actually converted them into a graph. So the way it works is the nodes of the graph represent the sentences, and two sentences share an edge if they have an entry in the matrix. and the weight of that edge is equal to the entry in the matrix. So just as a small example, we have this 3x3 matrix here that is converted into a graph like so. So you have this would represent sentence 1 here, and sentence 1 and sentence 2 are connected by an edge of weight 0.75, and so on and so forth. So once that graph is created, we use an algorithm called the PageRank algorithm. Now, this algorithm was originally invented by Sergey Brin and Larry Page, who were the original creators of Google. And what the PageRank algorithm originally did was it represented the internet as a graph and ranked web pages. So what we did is we applied this algorithm to these graphs that we generated instead. And what the PageRank algorithm does is it ranks these nodes from most important to least important. And the top 10 sentences from our PageRank gave the summary of a document. And then obviously with a summary, it's a little harder to sort of define what is like a right summary or a wrong one. So instead we came up with these 3 metrics. If you let n equal the number of n-grams at a human written summary R and a computer generated summary T sharing common, then we define recall as the number of common n-grams divided by the total number of n-grams in R, the human summary. Precision is the total number of common n-grams divided by all the n-grams in T, the computer summary. And the F measure is 2 times recall times precision divided by recall plus precision. And we tested these metrics for unigrams. So imagine instead of an n here, it's a 1 gram. And also for a longest common subsequence between the two.
Okay, and these are our results. So the first graph, R1, represents the common singular words between our text summarizations and the human summaries. And the second graph represents the longer sentences and group of words that are common within the two as well. And we found that the most important thing to look at was the recall. And this is because recall shows a percentage of how much the human summaries n-grams are also in the computer summary. And we found that the recall is pretty low between both of these graphs. And we came to the summary that this is most likely because of the difference between extractive summaries and abstractive summaries, being that extractive summaries, which is our text summaries, were taken off from the official shelter-in-place orders, whereas the human summaries are abstractive. So it's hard to match up those two exactly. And that also correlates with our precision score as well, which is probably why both of those tend to be low between these two graphs.
All right, so finally, we just decided we were gonna try and get some like sentences from all the computer generated ones and see if we could get some like common things between them. So in a way, sort of like summarizing the summaries. So what we did to do that was we created a corpus that was all the words from all the summaries. And then first we tokenized the documents into sentences. So each computer generated shelter-in-place summary was tokenized into sentences. And then each sentence was scored as the sum of the TF IDF weight of each word. So let's say a sentence had 5 words in it. The score of the sentence was the weight of all the TF IDF weight of each of those 5 words added together. And then what we did was we put a tuple that had the score in the sentence and put the tuple into a priority queue, just a regular one. So it actually has the tuples in ascending order. And the first 20 sentences served as the overall guide. So actually, this 20 sentences with the lowest overall score served as the summary. And the reason for this is because TF-IDF actually ranks common words lower. And we wanted sentences that were sort of common among the entire group of shelter-in-place summaries that were written. So we figured actually sentences with a lower overall score would prove to be a better overarching summary. So thank you for watching. We would love to answer your questions, but unfortunately we can't.
Yeah,
And
thank you.
yeah, thank you.